Okay, cool. So let's begin. We have a special session today. Patrick is going to talk about all sorts of Modal FRP. We have 2 talks from him, but this is the first one on a fish-style embedding of Modal FRP.
All right, thank you. So I'll talk a bit about Modal FRP. So, and in this first talk, I want to present an implementation of a Modal FRP language as an embedded language in Haskell. Right, so that's the for all part of the title. And I better start by explaining what I mean by Modal FRP. So the core idea of functional reactive programming is that we want to do functional programming with signals as first-class values. Right, so you can think of these signals as time-varying values that we want to manipulate. Right, so really think of them as denoting a function from time to values. Like this here, the signal of floating point numbers is really a function from time to floating point numbers, right? And we want to manipulate them in the usual functional programming way, right? That we have combinators that we define, higher order functions that we define to construct these signals and compose them and manipulate them, right? So, for example, a map function like this we would use to manipulate this signal by subtracting 1 from it, for example. All right, so that's the core idea of functional reactive programming. Now, this raises the question: how do we actually represent these kind of signals? And there's different ways of doing this, and I'm just going to show you one. And that's this co-inductive definition of streams, right? So a stream consists of 2 parts. The head of the stream, which is the value of the signal now, and then the tail over here is the future state of the signal, right? And so with this kind of naive encoding, we run into at least two problems. So we might be able to write programs that are not causal. So these are sort of broken in a very bad way because they sort of they define a signal whose value now might depend on another signal, the value of another signal in tomorrow, right? So we actually can't run these programs. So we should definitely avoid these, like this clairvoyance function that just throws away the head and just immediately returns the future state of the signal. That's a big no-no. Another problem is kind of the opposite, that we sort of allow too much memory, that we sort of look too much back into time, and that will lead to space leaks, like this leak function down here, which takes a stream and moves it arbitrarily far into the future, right? So this replicates the stream in every step of this new stream of streams that we define. So in order to actually run a stream like this, we would have to buffer at every step, so the whole history of the stream, right? So this will eventually run out of memory. So we want to avoid programs like these. And so there are different ways of avoiding these, and one is to use modal types. So we basically take LTL, linear time logic, and use it as a type system for our programs, right? To capture the passage of time in our functional reactive programs. And so this idea goes back to 2012. And so essentially we were able to use types like this here, this later A, right? So, and the circle here is the later modality from LTL, right? So, and a type like this classifies data that is of type A, but is only available in the next time step, right? So we say something about also when data is available. Now we can go ahead and take our type of signals, or streams here, this representation, and insert this later modality to really express this temporal dependency, right? Where we say, okay, the future of the stream, the future state of the stream is available only in the next time step, right? So now if we unfold this co-inductive definition, we really see sort of how time, how the stream evolves over time, right? We have a value of type A in the beginning, and then time passes, it's the later, then we get a new value of type A, and so on and so on. Right? So this is how these streams work. And then we have accordingly typing rules that will ensure that our programs are causal and they don't have space leaks. All right, so we can do this with a language like this. Now the question is, can we also embed this in a mainstream language like Haskell to actually use this? And this has been a very successful approach in implementing function-active programming languages, right? So to shallowly embed this in, say, Haskell, right? Because you get sort of access to the whole ecosystem of this language by seamlessly integrating with the host language. And this has been very successful for languages like Yampa, right? Where the approach they take is instead of taking the signals as the primitive, they take signal functions as primitive. So you can only define signal functions and then make sure that you cannot write any of these bad signal functions that are non-causal, for example. Right? A different approach is carried by FRP now, where you still have access to defining these kind of signals as primitives, but the library only exports sort of a carefully selected set of combinators that makes sure that the only signals that you can produce are causal and don't leak memory. Right? So this is all nice and well, but this won't work like this for Modal FRP because it's type-based, right? So it's more difficult to embed a language like this in a language like Haskell, right? Because it relies on rather interesting rules, typing rules, right? So that are rather non-standard. For example, we might not have a rule like this, which might seem odd, right? Just because we have a variable x in the context gamma does not mean that we're allowed to use it. It might seem silly, but think of this variable x here might refer to a value in the future, right? So we better not use it now to avoid non-causal programs. Or it might refer to a value from the past. And so by using it now, we run the risk of leaking memory. So you have to find a way of doing this. And this is what we did with this language Ratus, which is an implementation of Modal FRP language embedded in Haskell, right? So that's what I want to present to you today. And so this is also based on a sort of solid foundation. So it's based on a core calculus, which we also have formalized in Coq, so they actually prove all these operational properties that we want to have from this language. Right? And so the implementation itself is based on this very simple observation that every Ratus program is also a Haskell program. Just not vice versa necessarily, right? Not every Haskell program is also a Ratus program. So we also rely on a compiler plugin that checks these typing rules, these stricter typing rules for Ratus and rejects all those Haskell programs that are not Ratus programs, right? So the Ratus implementation consists of these two parts, right? It's a Haskell library and also a compiler plugin. All right, and so the goal really for this project was to have a Modal FRP language that we can play around with and we can experiment with in a existing software ecosystem. So that was the motivation for doing this work. So let me show you how this language actually looked like. So this is how you would define how you would write a Ratus program, and it's just standard Haskell syntax. You would import some modules, like the first one here, we import the Ratus language essentially, then the stream library, so we can work with streams. Then down here we implement this increment stream function that takes the stream as an input and just increments all the values in it. And you can see we can sort of seamlessly interact with Haskell, use the types from Haskell and functions that are in there in the standard library, so without any hassle. But for this to work, we have to sort of at the top here say, okay, we actually want to program in Ratus, so we enable this compiler plugin. And then down here, what we do is we say this inc function should be type checked as a Ratus function rather than just plain Haskell. So that's how you would interact with this system. All right, so here I've just copied the function inc to sort of look a bit more closely in how the function actually works, right? So what we do here is, so we take a stream as an input, The first thing we do is we do pattern matching on it, right? So we take apart the head of the stream and then the tail of the stream. So the tail is of type later stream of int, right? And then we produce a new stream over here, and the head is easily enough. It's just adding 1 to x. And then for the tail, well, we have to produce something of type later stream of int, right? We have to produce something of type later something. And this is where the delay comes in. So the delay is the introduction form for the later modality. Right? So what we do is the delay does is it takes a term of type A and delays it and produces something of type later A. Right? But in order to do so, it inserts this this tick here into the context. Right? So this is the Fitch style typing that was mentioned earlier. And so what it essentially does is it says, now this T has to be typed in this new context. And this tick here is essentially evidence that time has passed, right? The clock has ticked, and T can make use of that, right? And in general, the context, gamma, may contain several of these, right? For example, here is an example that we have first A and B are in the context, then time passes, then we have C in the context, and so on and so on. Right? So in particular, for example, E here is 3 time steps younger than B over here because there's 3 ticks in between. And so we keep track of the age of our variables in the context. And we can use that fact that we have these ticks in the context when we want to go back in time again. And that's what we do with advance. So advance is sort of the inverse of delay. So what it does is it takes something of type later A, so something that should be executed in the later step, and uses it now in the future and gets something of type A. Right? And it can only do that if it knows that we are already in the future. Right? We are already in the future for which this T was meant to be executed. Right? And so advance will consume this tick here. Right? And in particular, it forgets all the stuff to the right of it, because this refers to data that was sort of accumulated in the future, and now we're going back in the future. And so now we use that down here in the definition of inc to produce this argument to the inc function, which has to be of type stream of int, but xs is of type later stream of int. Right? And it makes use of the fact that the delay has introduced the tick to the context. All right, so this is how we interact with the circle modality, the later modality in Ratus. But that's not the whole story. We also have to be careful about memory leaks. Right? That was one of the motivations. And so this function here, I mean, it looks innocuous, this const function. What it does is it takes an argument of type A and just produce a constant stream that just replicates this argument over and over again, just a constant stream. Right? It looks rather innocent, but we should not allow this to type check. So because this will actually leak memory, right? In particular, if A here is something time variant, like a signal, that is itself a stream, right? That is actually the same function that I earlier had in earlier slides that I called leaky, but where I specialized the type here to a stream type. Right? The problem is if that's something like a stream and I push an arbitrary file in the future, this will leak memory. Right? So we should not allow a function like this in general. Right? And how does the typing system prevent this? Well, remember this is the typing rule here for delay, and it inserts a tick into the context, right? So saying that time has passed. But let's look now at the typing rule for variable introduction. So what it means now here, the x here has to type check in this context that contains the x in the context, and also a tick token that time has passed. And the problem is that this won't type check, because this is now the variable introduction rule in Ratus, right? So we can use a variable x that appears in a context, but only if either there is no tick to the right of it, so no tick here in this gamma prime. That's not true here. We actually have a tick right next to it. Or if A happens to be a stable type. Now you can think of a stable type as something that is sort of cheap to store in memory over time, right? Something that is not time dependent. And this includes like something like base types, product types, sum types, something like that, right? In particular, not the later modality itself. So anything that is not sort of time dependent. And we don't know that A is a stable type, right? So that's why we cannot use A here, right? Neither of the two conditions is fulfilled. Right? And the idea is we should not move X into the future if we don't know that it is of a stable type. So what we can do instead is rely on Haskell's type class mechanism and say, well, A better be a stable type, right? And this now type checks, right? So we can give this const function this type with the constraint that A is stable. So this works now. Okay, so stable types will ensure that our programs won't leak memory. But it's also rather restrictive because it rules out some programs that we rather wanted to write, for example, map. So map doesn't work anymore, which is really too bad. And the problem is that function types are not stable, right? And why are they not stable? Well, what are values of a function type? They're closures, right? And these closures might contain values of arbitrary type, in particular non-stable type, right? So we should not allow these values to be moved arbitrarily into the future, right? So that's why they're not stable. Now the problem is if f here, our f here is of a non-stable type, well, we can't use it over here because it's in the future, right? It's underneath a delay, right? So there's a tick between the occurrence of f when it is bound and f when it is used. So time has passed, so we're not allowed to use it. But we can turn any type A into a stable type using this box modality. Now, box is again taken from LTL, right? So think of box A being the type that classifies all data that is available now and any time in the future. So it's the always modality, right? And so we can turn a T of type A into type box A, which is then always stable. So box A is always a stable type. But we require the T be type checkable in this revised context gamma box. And so basically what gamma box is taking gamma and stripping out all of the dynamic parts, all of the stuff that is non-stable, so all variables of non-stable types, and all of the ticks, right? So there's nothing temporal in there. Only the stable stuff remains in there. Right, so that's the idea of boxing values. Now if we change the type signature slightly and make this into a box type, then this will work, right? So we have now that f is of type box A to B, and so it's in scope over here. So that's fine. And the only thing that remains is sort of that we can actually use it. So we also must be able to unbox values like this, right? So unbox is very simply turns something of type box A into A, and we can use this up here to turn this boxed function into an actual function that we can then apply to an argument x. So that's basically the language that Ratus supplies. So we have a circle modality and a box modality that we can use. Oh yeah, and I have implemented a game in this language. It's a very simple game. It's like a Pong, just with one paddle. Works like this. And so how does it work? Well, Pong is just a function that takes a stream of inputs, just as keyboard inputs, and it produces a stream of a pair of a position. It's a two-dimensional position. That's the position of the ball, and a floating point number. That's the position of the paddle that moves. And then we just have a function that defines the position of the paddle like this, and a function that defines the position of the ball like this. And then we just zip them together up here, the two things, right? And as you can see, so the position of the ball depends both on the input that we give, because we might want to reset the game and so to start from scratch, but also on the position of the paddle, right? So it's very, very sort of compact code that you see, and it uses lots of high-order functions like map, scan. I think also zip width is somewhere in there. So that's the kind of programs you can write in this language. All right. So how is this actually implemented? You might wonder. Well, as I said, the implementation consists of two parts, right? It's a Haskell library plus a compiler plugin to get the right language out. And the Haskell library itself is really simple, because all it needs to do is define the syntax of the language, right? It defines our later modality, sort of approximated by an O, and the box modality, and then just the delay and the advance primitive for the later, and then correspondingly the box and the unbox, and that's it. Right? And all the interesting type checking is done by the plugin. And similarly, stable. Stable is just an empty type class with no instances, and the plugin will take care of implementing this in the right way. So all of the smarts is sort of in the implementation of the compiler plugin. And to explain how this works, I'll just show you a very much simplified overview of the compiler pipeline of GHC. Right? So we start out over here on with the Haskell source that gets parsed into an AST. And then we type check that into type annotated and AST, desugar this into Haskell core, and then GHC will do some passes over that to simplify, to optimize, and then from that it will generate the executable code. Now, what Ratus does, it hooks into various parts, right? So these are the ones are highlighted here in red. For example, here during the type checking phase, we also supply a custom constraint solver that solves all the stable constraints, so checking that types are stable if we require them to be stable in certain circumstances, right? And then over here we give the scope check. What it does, it actually checks the stricter typing rules of Ratus, make sure that this is true. And then after desugaring, there's two extra passes. The first one called single tick. That requires a bit of explanation. So the language that I showed you, right? Remember, you can have multiple ticks in the context that denote the passage of time. So that's all nice and well if you want to program, right? You can sort of look ahead several times in the future. But if you actually want to run these programs, they are prone to memory leaks. So we cannot guarantee that you don't have these memory leaks if you have multiple ticks. Only if you use at most one tick. But you can always transform this multiple tick calculus into a single tick calculus. So you can always transform them. And so this is safe for memory leaks. And that's exactly what's happening here. And then finally, I haven't really told you about the semantics of Ratus. It turns out Ratus is a strict language, which Haskell is very much not. So what's happening here is a transformation of the Haskell core, this reduced intermediate language, into a form that actually respects the semantics of Ratus. So it's actually strict by default, and only the box and the later modality is lazily evaluated. All right. Let me talk a bit about the meta theory very quickly, since I'm also running out of time. So as I said, sort of Ratus is based on a core calculus, which I call lambda tick, which I have formalized in Cog, and also prove some semantic soundness property, so that actually won't crash. And from this semantic soundness property, it's essentially a proof using a logical relation. We can then derive the actual operational properties we're interested in, meaning causality and the absence of space leaks. Right? So these were the two problems that I mentioned in the beginning of my talk. And we also prove productivity, so that each computation step is terminating. All right. I also wanted to talk a bit about the operational semantics, but I'll skip, in the interest of time, I skip over it a bit. The important bit is, though, that it uses a store to store delayed computations. So whenever we do a delay, we store that in some kind of heap. And this heap, in general, can contain sort of two phases. So a heap that stores computations that are delayed for the next time step, so that's this later heap, and then computations that have been delayed previously and that are now safe to be used now. Right? And the important bit is, so this is how delay and advance interact with it, but the important bit is this here, is that whenever a time passes, so whenever the clock ticks, right, we move from a store that looks like this, right, this is the now heap, this is the later heap over here, to a heap that looks like this. So the later heap is sort of promoted to the now heap, so on the next time step we can actually read from it, and the now heap is just garbage collector is just gone. Right? So that by this construction, the semantics itself is, by construction, has no space leaks. Right? And then the proof is merely showing that this won't crash. Right? So that's taken care by the semantic soundness property. All right, to conclude, what else is there? So you can try it out, Ratus. You can just do a cabal install Ratus, and then you're off to the races, and you can play around with the language. There's some more stuff about the meta theory, how that works in the paper, and it also loads more examples there. So in particular, there's an FRP library, like a straight FRP library to do this kind of programming that I showed you with the game. There's also a Yamper-style FRP library implemented in Ratus, right? So we can actually also do sort of errorized FRP in this language, and also this more details about this game that I showed you earlier. And that's all I had. Thank you.
Yep, good. Cool. Great.
So there was one thing I didn't understand there. You showed us the map function, and you explained that there was a problem because we have the parameter f now, and we need it in the future.
Yeah.
But we also have map now, and we need map in the future. And yet you didn't do anything to enable us to use map later.
Right. Excellent question. Yeah. So whenever you have sort of defined functions, sort of in a global space, like top-level functions, right? They will always be stable because they have nothing else in the context that might be time dependent, right? If you remember, so this is how we in order to make things stable, we box them, right? Where is it? Here, the box, right? And all it does, it takes the context we are currently in and removes stuff from it. If you have top-level functions like map, there's nothing in the context, right? Other than other top-level functions, which are also stable. So top-level functions are by default stable, so we can use them anywhere.
Any other questions?
I'm curious, how do you actually check this box operation?
How do I check what?
Like, how do you actually type check this box?
Right. So in the compiler plugin, right? So what I do in the compiler plugin is basically I traverse the AST and collect this context here, right? So things that are variables that are bound, and then whenever I want to type check a box, then I just remove the offending stuff from that context. So I mean, I have the AST at hand in the compiler plugin. So there's no magic to it. I really just do what you would also do in sort of a standard standalone language, traversing the type the AST.
I had a question. Have you thought about putting mutable references or mutable arrays? How that would interact with the stability?
Oh, I have not at all thought about mutability. No, this is all pure. And actually, so it crucially depends on being pure, right? So I showed you the one of the steps in the end was this turning into a multiple tick calculus to a one tick calculus, right? So that's a program transformation, and this depends on it being pure.
Great, thanks. Thanks, Patrick.